Okay, so it's my great pleasure to introduce Ingo Grvemeyer. Just a few words of his career as introduction. Ingo did his PhD on the Atlantis meteor seamount complex using seismic and satellite altimetry data, finishing in 1994. In 1997, he moved to Bremen University. Subsequently moved in 2003 to Kiel, where he's been ever since. He's, I believe, a senior research scientist at the GEOMAR, but also an adjunct professor at the University of Kiel. And today's talk is on oceanic transforms. And well, I'll let you get started, Ingo. Thanks.
Yeah, just try to get this thing out of, now it's out of the way. So that's better. Yeah. Neil, thank you very much for inviting me and everybody to join the presentation today I'm giving. So of course, like always in science, that's not entirely my own piece of work, at least not everything. So I first like to thank a few of my collaborators like Lars Rübke, Jason Morgan, and Colin Divey and Kartik Iyer. And also I have some more recent features which go into the presentation very briefly in the end. So I thank Jiku and Shibao, who both have helped a lot by helping with some gravity field anomalies from thermal models. So actually, I in the official talk I gave another subtitle that may indicate that transforms are a little bit different than we have envisioned. So. But generally, I just like to call the talk kind of Oceanic Transform Faults Revisited, because in the beginning of plate tectonics, they have been whatever, just introduced. And then I think we spent reasonable little research on transforms in the past. So, but I think there's a big future topic which may come up. So first, I like to give a brief introduction in different terms like fracture zones, transform faults, and a little bit indicate how we believe they are operating, at least in the past. So then I will go into the presentation and also a paper which we recently have been published. So therefore we will visit 41 transform faults. I'm not showing all of them, but just some examples. And we will evaluate some of the processes we believe we see in those bathymetric data from the transforms. And we will do that first by kind of using numerical simulations. And then we look a little bit on bathymetric maps, checking up more details, which I indicate here as a kind of geological point of view. And then we come up with a kind of new conceptual model we derive for the transform faults. And in the end, I try to put some ground truths or some kind of more modern, different data going beyond the paper. First, I use gravity field anomalies, and then I'll check a little bit on magnetic anomalies, and it will conclude in the end. So oceanic transform faults and fracture zones, they are very known for a very long time. Actually, the fracture zones have been discovered before plate tectonic has been established. So Bill Mannard found them in the Pacific Ocean. We see here a map of the Pacific Ocean. And we see here this big, huge fracture zones, and they're run through the entire Pacific basin. So this is a Clipperton zone, which actually is about 10,000 kilometers long. So one of the longest features we may have on Earth. And they have been recognized before. For example, the spreading centers have been really kind of come into the story. They are reasonably complex features. Big bathymetric anomalies and like described here as a kind of seamounts or trough and ridges. But of course, nowadays we know that fracture zones are linked to the spreading center over here. So when linked to a spreading center, the features a transform fault. So I first have a brief look on how they behave on the continents. But just very briefly, in principle, the transform is a strike-slip fault. You see here two different pictures, one from both from the San Andreas fault. You see here, for example, a river. So in the past, it went straight ahead. Then the transform motion kind of offset the river to the side. So here is a kind of previous one. So this clearly indicates that we have a lateral strike-slip fault. So, and it's not yeah, it's kind of step-like fault in here. So that's a kind of view along the transform fault. We see kind of ridge-like feature here where the transform runs here. And actually the transforms are considered as a basic part of plate tectonics. They are one of 3 type of plate boundaries. Of course, everybody knows that. Yeah, and they are kind of so-called conservative plate boundaries, which indicate that crust is neither created nor destroyed. That's the kind of key aspect we touched later today. So transforms are reasonably global phenomenon. They occur both on the continents, like the Dan Andreas fault over here, or we have in the Alpine fault in New Zealand, or we, for example, we have the Dead Sea fault or the Anatolian fault in here. So that's the kind of key continental transform fault. And then we have lots of them in the ocean. And you see they are kind of offsetting the mid-ocean ridge. I come back to that in a minute. And then we see the trace of the transform fault in the ocean basin, that are the fracture zones. So fracture zones we don't see on continental transforms, of course. So why are transforms there at all? So they are a kind of inherently related to plate tectonics. So if we move a plate on a sphere, for example, then yeah, and the plate has kind of irregular topography or edges, then we have first the spreading segment, and where those are offset by their geography. So we have the transform faults you see here. And transform faults are actually kind of small circles with respect to a pole of rotation. You can see that here, for example, something I generated in the past for lecturing. So if I take the trend of the transform fault and I make a line normal to that, and then I put a kind of straight line, that's a Mercator projection there that looks a little bit curved. So all lines kind of basically meet in one point. I can do something similar to a slip vector of an earthquake and a transform fault going normal to the slip direction, then we end up again to the pole of rotation. So this kind of transform faults are very clearly a major part of plate tectonics. And so now we move more to the ocean. I will describe briefly how they look like here. So of course, the structure I will touch today are basically so-called ridge transforms. So they should behave very similar to continental ones, except that they have their trace, so the fracture zone. So the transform is the part which is tectonically active with earthquakes, and then we go into the kind of passive fracture zone. So here plates move in different directions, here plates move in the same direction. Of course, since Wilson introduced the idea, I think that is well established. Yeah, so and there are key features in the topography. You see that here they offset the mid-ocean ridge by very long distance. I think the longest one is here the Romanche transform in the central Atlantic Ocean, which offset the mid-Atlantic ridge by about 800 kilometers. So I think our point of view on transforms is very kind of based on the nice maps Murray Saab generated. And like here, the one on the Atlantic. So at least that was what shaped my point of view of the ocean basins and also transforms for a very long time. So again, in the mid-ocean ridge, and we see the spectacular offsets here along this transform fault. And then we see that the mid-ocean ridges are the shallowest part, and things get deeper when we move into the ocean basins where the lithosphere is much older. But we also have to keep in mind that these maps are generated by real data, seafloor topography, but then there's also kind of artistic part in there where coverage was too little. So that was kind of invented to fill the gaps. So, and I think that's still the concept which we have in mind when we talk about transforms. You see here a kind of out of the textbook, for example, still the mid-ocean ridge. Then we have the transform is here, then we go into the fracture zone. So, and we see that they're dominated by the same features we could see in Murray Saab's maps, so which mid-ocean ridge crest, and then a continuous subsidence in both directions. And also a concept like here on oceanic core complexes in inside corner and outside corner settings by Brian Tucholsky in Jian Lin basically is still the same. So we have the mid-ocean ridges offset by transforms or secondary transform ridge crest discontinuities. And again, but still we have the subsidence which basically dominates the entire structure. And please keep this kind of concept in mind. And I will now move ahead to some, and what's not in this concept, which will be at the heart of the presentation, are transform valleys. You see that the transform is a very simple boundary. This is already compiled by Jeff Fox and Gallo in years, maybe 30 years ago. So it's a concept they have on transform faults. We have a very prominent valley, and the valley continues into the fracture zone. That's also something we have to keep in mind when we look at more modern bathymetry in a minute. So what we have done in our paper, so basically we have revisited now lots of transform faults in different oceans. You see them here kind of numbered. So we have here the East Pacific Rise, the Southern East Pacific Rise. We have some on the Nazca spreading center here. This is the Chile spreading ridge. We have the Mid-Atlantic ridge over here. It's a slow spreading one. This one has been fast spreading and intermediate spreading rates. And also here's another intermediate spreading rate ridge where we have a couple of transform faults, the Southeast Indian ridge. And we have also some data down here on ultra slow spreading ridges, the Southwest Indian ridge. So I try to move that away. So that's a compilation we have been made. So for all ocean basins and transform faults with all different spreading rates. So, and what I will show you in a minute is that some of the concepts we see that they're not really in agreement with the ideas of plate cooling. We will see also there that at ridge transform intersection, there's a major change in seafloor bathymetry. And we think that it all indicates that the transforms are not really, at the oceanic transforms, I have to say, are not really conservative plate boundaries, but there's a different flavor coming in. And yeah, I will indicate that later today. What's happening now? Okay, so now I just like to share a few examples from mid-ocean ridges and transform faults. Maybe I have to guide you carefully through some of the figures. So the one limb of the spreading axis comes in here. The other one goes out here. So this one is a kind of crest, like this has a kind of median valley. This is the East Pacific Rise offshore Mexico, and we have here the transform boundary. So the transform itself is a kind of a trough. But then when we go towards the mid-ocean ridges, we see that the trough is not really continuous in here. So basically the transforms look a little bit like being sandwiched in between two different segments. It is a Garrett transform, one of the fastest spreading or slipping transform faults we have. The ridge comes in here and it goes out in here on the other side. And then we have a more complex shear zone in here. There's actually a short spreading segment in the middle. But again, what we see that very prominent bathymetric deeps in the center where the transform is located. And these deeps are not really kind of in the bathymetry if we move away to the older seafloor and away from the transform fault. So there has been two fast spreading ridge examples. Now we go to two examples from intermediate spreading ridges. This is just to the north of the Galapagos. The Galapagos Islands are somewhere in the south here. The mid-ocean ridge comes in here. Transform fault along this valley here, ridge transform intersection, and then we move into the other segment of the mid-ocean ridge. And again, we see here the very prominent low where we have the transform, and we don't really see that this low is continuous into the fracture zone, as for example, the concept I just have briefly introduced. And we see something very similar in here. This is now the Southeast Indian ridge. The ridge comes in here. Here we see something very prominent and lots of data that we have the kind of mid-ocean ridge curving into the direction of the transform fault. And we same see on the other segment. And then again, we have a very big trough in the center where the transform actually is operating. And also it's not just a kind of line like cut with a knife. It's a more larger valley-like feature which has been opened in here. So that have been the intermediate spreading ridges. Now we move to one of the best studied examples we have. It's the Atlantis Transform at the Mid-Atlantic Ridge. Here the mid-ocean ridge comes in here, goes into the transform fault, and then the other segment of the Mid-Atlantic Ridge goes up through here. So and here we see a little bit nicer because we have more coverage to older seafloor, that the transform again is the deepest part. Sometimes we have big, deep nodal basins. Nodal basins are the areas close to the ridge transform intersections like this one or here on the other side. But then we also see that we don't see this prominent feature of subsidence, which has been indicated in all the conceptual ideas, but that the fracture zone actually is much shallower over here. And yeah, so I come back to that also later in a minute. And again, what we have here, some example from the Southwest Indian Ridge is the Shaka transform in here. And on the other side, we have the Atlantis II transform fault here. So again, we see that we have a very wide and very deep transform. It's actually nearly 6,700 kilometers below sea surface in this case. And then again, if we move from the transform into the spreading segment, which goes over here and then through here, it's a little bit more complicated. But when we go to the fracture zone, you see that the fracture zone is much shallower than the transform domain. And the same one we see in here, that Atlantis II, again, transform a very deep basin and a very deep valley. And then we go into the ridge segment over here, and the other ridge segment comes in here. I'm not focusing now on the details of the bathymetry we see at ridge transform intersections. I come back to that in a minute. So this has been the kind of conceptual idea we have introduced in the past, so in '84 by Fox and Gallo. And this is a kind of modern type bathymetry we can nowadays obtain with good SWOS mapping data. That's one transform at the southern mid-Atlantic ridge. But I like the example very much. It shows the key features very nicely. So we have a very deep transform valley, similar to what has been proposed here. We also see that there kind of continuity to the fracture zone, but it's not really the continuity at the same depth, but seafloor gets much shallower in here. So now we'll show you in a minute some results from some kind of statistical study. So how we have done this. So this is just for getting the conceptual idea. All the 5 examples I have here are inside corners like this one over here. So where we see the ridge crest coming in, then we have the tectonic deformation zone. That's basically the transform fault. And then we have the fracture zone out here. So different examples, Clipperton, fast spreading, Flaming, intermediate spreading rate, mid-Atlantic ridge example, and Marion on the Southwest Indian Ridge, and again, the Atlantis II transform here. In all cases, we see that the transform is very deep and the fracture zone is much shallower. And what we have done now in a kind of statistical approach, we have now sampled for the transform where we have bathymetric coverage. We taken the depths in here, and then we have taken the depths out here and out here. So basically averaging, for example, in this example, depths in here, but of course towards the other ridge transform intersection, and then the depths out here. And when we compile this one and look into the data, it's looked like this here. The kind of now the statistical representation of the 41 transform faults we have been studying. And what we see and plotted in here, first plot, for example, the depths of the transform valley. It's kind of the average of all the data. And if the depths in the fracture zone would be the same, everything should plot along this kind of broken line in here. But we see that all 41 examples we have been studying in here, they actually are on the left-hand side of this line. This indicates that the fracture zone is much shallower than the transform valley. And that you could see also in this plot here, this is a delta depth, which something like how much depth change have been observed, but it's between a couple of 100 meters. And out here we have about 1.5 kilometers. And I think this guy is in the way, so you can see it better now. So it's a 1.5 kilometers over here. So we have a prominent depth change, and here we plotted that against spreading rate. So what I also plotted in here is a valley depth, where the spreading rate, we see that the deepest valleys are generally at the, you can see the color code over here. Southwest Indian Ridge is, for example, this orange type colors. This one is the slow spreading one, Mid-Atlantic Ridge, Central Indian Ridge. And then we go to the fast spreading or intermediate spreading runs over here. We see that the deep transform valleys are more prominent at the slow and ultra slow spreading ridges. And then kind of this deep valleys become less prominent, but they are still there. We see actually a much better correlation when we not plot that against spreading rate, but against the age offset. So we see a little bit more better kind of clustering of the data in this trend. So the largest age offset having the deepest valleys, but maybe that's not a big surprise. We have the strongest thermal contrast in this case. So this is the kind of the summary of all this kind of statistical approach. And now we take a more careful look what or what processes could control the features we have been seeing. And this is an approach done basically by Lars Rübke, Jason Phipps-Morgan, and Kartik Iyer. So they have been running this models. So this is now a kind of, they used aspect to calculate this. So the important one at the top, we have the mid-ocean ridge. Then we have a perfect strike-slip boundary over here, and the other segment of the mid-ocean ridge. So we use a rheology, it's kind of plastic brittle one. This is actually based on work which have been done by Mark Bain from Woodsole. He kind of introduced this kind of ideas how to model the transform faults, and we just built on his research and yeah, kind of went ahead from that. And so this is the kind of setup. So it's a real 3D model we are now looking at. And the important one is at the top, it's really a strike slip boundary. But to our surprise, what was been happening when we have running those models and we looked more what kind of features we see, that we have seen that actually some of this, or the main transform fault, which changes its orientation with depth. I show you the effects briefly in here. So the mid-ocean ridge, the top view transform simple strike slip boundary would be this reddish line here. On the left-hand side, we see the viscosity. On the right-hand side, we see the strain rate coming out of the model. And then we see here different lines in here, these greenish ones. This is at the depth of 2 kilometers, 4 and 6 kilometers. This is a case of a transform fault with about 90 kilometer offset. It's similar to a fast spreading ridge example. But what we see here now is that actually the top plate boundary is not really the plate boundary which we see at depth. So the kind of strike slip faults get more obliquely with depth. So we get a kind of extensional shear zone within the transform domain because we have different motion of the plate in different directions at different settings. I show you that in a minute. But the most important one is that the mantle flow is not mimicking the plate boundary at the surface. So important one, this 3D numerical modeling indicates that the strike slip boundary on the top gets kind of oblique at depth, and that causes some extension. I move you through this here. So the important one, for example, is that plates move in opposite direction beneath inside corners, causing the extension. Can you show this here? So this is a kind of transect we see, this broken line which runs through here. So from left to right, basically from west to east. And that is the same transect. We see where the ridge transform intersections are. And the color code in here, reddish colors move to the left, to the west, and the black colors move to the right, then to the east in this case. So, and you see when we're below the ridge, that actually a big portion here already moves in a different direction. And here the plate moves in the other direction. And indirectly, this effect causes some extension above that domain. And when we take the same idea and we look at a kind of 3D view, we see that what the consequences are. Again, surface plate boundary here. What's shown in here is first the depth to the brittle ductile transition in this kind of bluish to reddish colors. Red is deeper than the blue, and the green lines indicate the depth in kilometers. For example, here 3, 4 kilometers, 4.5, 5 kilometers. So you see that the tendency is gets deeper over here. We see the same greenish line here. So at the ridge in the inside corner, it's about 2 kilometers, and then we see that's getting deeper and deeper over here. So this indicates some amount of thinning, which we can also express as a kind of stretching factor, which I try to do in here. We see the stretching factor along the same line now. And we see here now how the stretching accumulates coming on. It starts in here, and then we get more and more stretching kind of as we move along this transform boundary here, where in principle, we would only have expected strike slip motion, but we see that this actually within the transform valley, we get a certain amount of extension. And yeah, so, and this actually indicates why the transform faults generates this very deep basin. So it's a consequence of the rheology and the moving plates, and then the interaction between two plates moving in different directions, causing the surface plate boundary getting oblique, which is a blue line in here at a certain depth. So if we now try to see that in the accumulative sense, so I will now show you some profile, which is here kind of north-south profile in here. So that's outside of the domain. We don't get any stretching anymore. So that's it. But that's how the stretching has been accumulating over time. This one is in the inside corner setting, this side in the outside corner setting. And we actually see that, for example, the inside corner has experienced much more thinning than the outside corner. And this is what we are basically seeing, that we have a prominent thinning and causing this very deep valley. And we actually use this kind of area which has been generated in here to look also at different transform settings with different spreading rate and different age offset. That's a kind of summary of the outcome is here. First, of course, what we may expect when the spreading rates go down and the age offset gets larger, we have first a kind of brittle ductile transition going deeper into the model, so going to greater depths. And what we also see that the amount of thinning goes up. So this is a kind of tectonic thinning, similar to how it's defined in here. So therefore, it's a kind of funny square meter unit, but still it's indicated the area which has been generated. And we see a similar trend that we have more tectonic thinning when we go to larger age offset. And that would indicate why we have the deeper transform valley. So we have more thinning in those areas. Now I like to take, so that was maybe one explanation why transform valleys get so deep, but maybe you are wondering what's happening actually that the transform valley thereafter gets much shallower. This is nothing which we can derive from the numerical models. So our numerical models do not include any magmatic melt migration. So, and that's actually the key feature we believe is causing the depth changes, ridge transform intersections. Therefore, I will show you now some examples. This is, for example, the Clipperton transform. The transform moves through here. Here's the spreading segment. And the important one seems to be that the spreading segment interacts with the transform domain. We have this J-shaped features. So that, of course, they are J-shaped because the stress rotates very quickly from the kind of extension mode to a strike slip mode in here. So, and we see that in the bathymetry, this J's. And what we also see that there seem to be lots of additional magmatic material. For example, we see kind of circular, kind of seamount-like features in here, volcanoes here. So while this one, the J's could be kind of dike propagation, we believe that all the circular volcanoes are fed by melt coming from below. So maybe we have also not just a diking, but maybe we have some melt migration, for example, along Moho, and then it kind of rises through the crust and causes some extrusive magmatism. But the key feature here is, again, that we see this very prominent magmatic features in here, basically filling in the transform valley. So this is a Clipperton, and now we have a southeast Indian Ridge example. Transform is in here, so you see it here, and then again we see this, as we go to the spreading center or the ridge transform intersection, we have this J-shaped features. And then again, we see that basically here, this transform domain, it's kind of buried at the ridge transform intersection by additional magmatic material. In this case, we don't see so nice, this kind of circular seamounts like this one. There might be a few dotted things in here, but what we definitely see, we have magmatic material, which is kind of extruded onto even the older plate. It's covered lots of material on the older plate. We also see that in the case here. And some other example, this top one is just the fracture zone. So it's not active transform. We look basically what happened in the past. So the transform in the South Atlantic Ocean, where swath mapping provides complete coverage. This is the fracture zone valley. And when we look in detail again, also here, we see kind of fossil J-shaped features in here. And we see lots of material, magmatic material kind of extruding, or in the past, which has extruded into the transform domain, filling up the transform and having a different setting in the fracture zone. But again, here we see lots of kind of small seamounts. So this might not just be dike propagation, but also magma coming from below. This is now the Chile Ridge at 30° south, sorry. We see the same features, J's coming in here. And again, we see lots of material which actually extruded onto the older plate. But again, we also see here lots of circular features, seamounts. So again, we have certain amount of magma which might be kind of introduced by intrusions from melt, maybe rising from below Moho into the system. So here are some examples that this is not just something for fast and intermediate spreading ridges, but it's also a feature common at ultra slow spreading rates. This is a Southwest Indian Ridge example, 34 degrees east. Here's transform coming in here. The mid-ocean ridge is here, so the valley-like. Here's the mid-ocean ridge valley. But then we see in the outside corner always this very prominent J-shaped features. And again, we see lots of material which have basically filled up all the fracture zone, the transform domain in here. So we see that the same width which has been here, the transform, is filled up by additional magmatic material in here. So the features, as we have this J, we seem to have a kind of episodic approach or episodic mechanism. And this is again now fracture zones, so that's away from the mid-ocean ridge. So what's happened in the past, but again we see here this J-shaped features going in. That's still the Southwest Indian Ridge. So also here very nice J's. Of course we have time with not as much magmatism, but still also here we see kind of small scale volcanoes. We see here a very faint J, and also here we see small scale volcanoes in here. So that seems to be the same process at all kind of happening in all spreading rates. It's not just a process as previously described happening at fast spreading ridges, but also something happening at slow spreading ridges. I'll briefly like to summarize what we have found. So first, plate tectonics so far described transform faults as being conservative two-dimensional strike-slip plate boundaries. We think that's not entirely correct. So from the bathymetry, first we have seen that we have a prominent depth change, so by up to 1.6 kilometers, so that transform valleys are always much deeper than the fracture zones. So we need a kind of secondary process filling up the transforms. And yeah, and we see, or we think that that's done by two phases of crustal growth. First, as crust is in place at one inside corner, or at one ridge transform intersection, then it moves along the transform where it actually experiences tectonic extension. And then we have a second phase of magmatism at the second ridge transform intersection. And the numerical modeling indicates that while the plate moves along here, the plate boundary gets oblique. Here is a strain covered at a certain depth. You see that lots of strain is not along the strike slip boundary, but at greater depths. And this kind of triangular shaped area is the area experiencing most of the thinning in here, because plates there move at different directions. So there we generate all this thinning. Yeah, and this accretionary process, I like to focus in here in a minute. So again, the ridge axis in here, and we see that the J-shaped features all go into this filling up the transform domain. And we also see that the much of the volcanism seems to be well preserved in the outside corner, while the inside corner seems to be tectonically affected. This is, for example, the Chile Ridge, intermediate spreading rates, but also we see similar things at slow spreading ridges like the Kane transform, which caused a big inside corner complex in here. But if we move to the outside corner, we see also there's kind of J-shaped features, so indicating robust magmatism filling up the area here of the transform fault, getting distinctly different structure in the fracture zone. So this part has been published recently in March in a paper in Nature. You can see the results there. And now the remaining maybe 10 minutes, I like to spend a little bit on recent jobs we have done at GEOMAR. And I try to provide a kind of proof of concept. So this is ongoing work, which is not published yet. And yeah, so as I mentioned before, I had big help here with some calculations. But what we do now, we'd like to use the concept of mental residual mental Bouguer anomalies to look if we see some effects like that, which have been described in the bathymetry, also in the gravity field. So what we have done, we corrected the effect of the seafloor topography, the density contrast at the seafloor, and we compensated the effect or density contrast at the Moho, assuming a thickness of oceanic crust, a constant thickness of 6 kilometers. And then what I've mentioned and where I had the help, that we have calculated the gravimetric effect of temperature changes in the mantle. This have been kind of aspect thermal models. Shibuya was doing it, and Shikui helped to generate the gravity field from that. So just to give you some idea how that looked like in practice, first we had the compiled as bathymetry, and we had the predicted, no, not the predicted, we had the gravity field measured from a satellite. So I used the Central Grid, latest version 23. And what we have done, first we had the bathymetry, and then we a little bit regridded that at a little bit lower resolution. I used about 0.5, I used 0.5 minutes resolution. And then we used to fill in some of the gaps to have the best gravimetric correction we could do. We filled that in with predicted topography. And when we combined both this grid with the other one, so the gaps you see here have been filled up. And then in the next approach, we kind of calculated the effects of the seafloor topography. And you see here the effect of the seafloor topography with its density contrast at the seafloor. That is the effect of the MOHO boundary with a density contrast there from crust to mantle. And down here you see the thermal effect. To illustrate better the seafloor bathymetry, all these grids are illuminated with the seafloor bathymetry. You see, for example, the abyssal hill fabric in here, which won't show up in the data elsewhere. Otherwise, but so it's much easier to see how that's related to the geometry of the mid-ocean ridge. So when we apply all these three corrections, so then we get the mantle bouquet anomaly, which top here. So that's the Atlantis transform in here, mid-ocean ridges. We see this kind of bullseye anomalies, which have been described in the past. And when we also compensate for the thermal effect, then we get the anomaly, which we see down here. So for those not too familiar with the concept of mantle bouquet anomalies, so positive anomalies indicate thin crust and negative anomalies indicate thicker crust. So in this case, if we come here from the transform and move into the fracture zone domain, we see kind of positive anomalies going to negative anomalies, precisely what we have been described. The most area which mostly affected actually by thin crust would be the inside corner, but the important one for us here is the kind of transform transition to the fracture zone. This has been one example. We try to do that for the other example. This is Marie Celeste transform in the Indian Ocean. I'm not going into all the details, but we have similar features in here. Positive anomalies along the transform and in the inside corner settings. And then we go for negative anomalies in the fracture zone domain here and on the other side. So similar features we have seen, and this was an intermediate spreading rate example, transform in here, fracture zone out here, bathymetry, and we see very similar features here in the mantle bouquet anomalies or residual mantle bouquet anomalies, negative anomalies, and more positive values in here. But we also see that the effects of changing in mantle bouquet anomalies going from the transform to the fracture zone, they are much more prominent at the slow spreading ridges. So important one here to take away that it looks like that at least for these examples we have been studying, that there seems to be the effect that we really have a thicker crust in the fracture zones and in the transform faults, which have been predicted by our bathymetric compilation and by the numerical modeling. So now, as the last two slides, I like briefly to go into magnetic anomalies. Maybe we could find some evidence for the idea we have been presenting. So if we go to the normal scenario, kind of transforms, turns into a fracture zone without any magmatism, we may have a scenario something like that. First, the magnetic anomalies here as a ridge crest. So then I indicated positive, negative, and so on, just to have a few reversals in here. So this could be either like this, or it goes directly towards the plate boundary, which would be the strike slip fault in the minute. Alternatively, we may generate something like this. So if we have a setting where a transform would dominate by ridge transform intersection magmatism, I would guess that we should have kind of spreading anomalies hitting the other side of the valley. So the entire valley should have the same magnetization and not something like this one in here. So we have not too many areas with dense enough magnetic data to do a good grid, but in the past, a swath mapping system did not record so much wide swaths as today. We had a much denser spacing. For example, here for the again the Atlantis Transform. Down here we see the grid we get from those data. So now I have plotted in here the same isolines on both plots. So this is a ridge transform intersection. And now we look into this transform domain over here. First, we see a very big magmatic activity here at the outside corner. That's domain in here. That's kind of consistent with a very magmatically active outside corner magmatism. And what we also see, if we look carefully here for this anomalies, here you see this bathymetric anomaly here, which is the bluish one outlined here. And to my eyes, I would say that the magnetic anomalies goes all the way through the fracture zone, hitting the wall of the older plate on the other side. The same one here with this kind of negative anomaly, positive ones. Also this one kind of has filled up or propagated well into the fracture zone. So this concept seems to be correct, that's all the magmatism here has been filled up the fracture zone. Looked a little bit more complicated on the other side, but here we see kind of J-shaped features. And it's, to me, it also indicates that we have a similar process that the transform here has been, again, filled up by rich transform intersection magmatism. And we have another example. The magnetic data are not as good. This is the Oceanic graphite transform also on the mid-Atlantic ridge. So we have the median valley going in here. Here's the Bruce prominent magnetic anomalies. Then here's the other ridge segment goes in here. Again, we see a very prominent magnetic anomaly, which indicates that the outside corner is magmatically more robust than the inside corner. And the magnetic data are not as clear, but I would think that we see here in this range here, where we have also these ridges coming in here, the ridges in here, the ridges are the same like here. We see that the spreading anomaly seems to go all the way into the transform fault, filling it up. And on the other side, we see something similar as for the Atlantis. In this case, we see some J-shaped anomalies going into the fracture zone, but filling the fracture zone up with magmatic material. So to me, this is also kind of indicates that the concept we have been proposing might be correct. But of course, we need to be a little bit careful with these magnetic anomalies because they have been gridded and the track spacing might be too wide, so we still have some artifacts. But overall, I think they nicely support what I've been indicating. Maybe just briefly to conclude what I've been indicating today, that oceanic transform faults, to our point of view, are not conservative plate boundaries. And the other most important result is that fracture zone seems to be significantly different from the crust which we find along transform faults. So we have a prominent change. And what we propose for transforms, that we actually have three distinct stages of formation of crust. First, we have asymmetric production of crust at ridge transform intersections, and where we have a kind of staff magmatism at the inside corner and more robust magmatism on the outside corner. That also indicates why these J's kind of survive on the outside corners. And then in the inside corner, which has been indicated by the numerical modeling, we have very much extension there, so which actually causes the transform valley, while the crust is moved in a strike-slip sense along the transform fault. And when the crust actually reaches the second ridge transform intersection, then we have a second form of magmatism filling up the old transform domain with new magmatic products. And we also think that we have a considerable amount of intrusions there in the system. This is kind of illustrated in here for the Kane transform again. And there's also a kind of field data available from seafloor imaging, kind of photos, mosaics and things like that, and from rock sampling, which seems to indicate that all outside corner domain is magmatically accreted crust, while the transform domain is more complicated and tectonically disturbed crust. So that's actually what I like to show you today. So the kind of new concept we have been shaping for transform folds. And yeah, we think there's lots of new research targets we have to tackle to really confirm that the concept we have been shaping based on bathymetry is really a robust magma mechanism and not just a fancy idea. So thank you very much.
Well, thank you, Ingo. Very good